Okay. So today's colloquium speaker is Charles Lin from the National Cheng Kung University in Taiwan. And Charles did his PhD in 2005 at the National Central University in Taiwan, and he did most of his research work for that as an HAO Newkirk Fellow from 2001 to 2005. And after he graduated, he spent 2 years at the Taiwanese National Space Organization, and then after that, since 2008, he has been a professor at the National Cheng Kung University, and his main research is in various sorts of ionospheric modeling and also some data assimilation, and he will present today on towards ionosphere forecast using COSMIC-2.
Thank you. Thank you. Um, it's my pleasure to come back to give a HAO colloquium as a former student. This is my first time to have a HAO colloquium. So I will talk about the ionosphere modeling. This is a composed figure of the data assimilation output of electron density in red color, plus this blue color are the plasma bubble observed from our images. And that six little guys are the COSMIC-2 satellite. So I'll talk about what kind of observation from spaceborne and ground-based GPS can improve the ionosphere modeling through the data assimilation, and what are the difficulties. So when I was a student, we were during the October 2003 superstorm period. At the time, I remember every other week we have a major magnetic storm, or very frequently we have a storm. So at the time, a lot of observation depend on the global ionosphere map built from hundreds of ground-based GPS observations. As you can see, this is a pre-storm condition of the ionosphere, and during the main phase of the two storm bursts in the October 2003. These are the by knowing more ionosphere physics in the evening ionosphere. And a lot of the paper from Tomoko and students and our team members have used the same approach. And I want to show you that if you look at this is again the model standalone run, you will see that the altitude model is very different from Weimer, and it results in very different structure in the prior state. For example, for this Helix model, you have this tail in the evening sector, but it's much weaker compared to this Weimer forcing in high latitude. And when it comes to the assimilated result in the measurement update, this kind of feature will stay. It will not go away quickly. But for those of area that the structure are similar, they have an intensification of the electron density because of observation show that the stone main phase, positive stone. I will show you the real observation of it. This is the March 16, 2015, a day prior to the stone, from UT 10, 12, 14, all the way to 23. And you will see this the equatorial anomaly of electron density in the equatorial ionosphere as a main feature of it. And during the stone time, it will look like this. You will see the clear enhancement in the low latitude region. Plus, you see the negative stone, the decrease of the TEC in the high latitude if you compare these two. So the gradient will be sharper than the quiet day. Okay. And I would like to show you that for this stone event, there's two periods that shows a positive TEC. One is around 12 UT, when it is at the daytime of the Europe, and the other one when the daytime comes to the roughly come to the U.S. American sector, you see another strong positive stone. There's two phases, and you see this plasma plume, ionosphere plume structure a little bit show over here, okay, at the east coast of the U.S. Okay. So how the assimilation model produces the result? I'll show you the movie. I'm sorry. Okay, showing you the control run at the F region of the ionosphere, electron density for Helix forcing, Weimer forcing, and we also plot out the eastward electric field over here. And these two panels are the data assimilation results. What the major difference is that you will see the overestimation of the positive stone for the model standalone, and you will see the larger east-west stretch of the electron density during the main phase of the magnetic zone and also electric field. I will show you some snapshot over here. So this is a snapshot at 16 UT. So when you look at the Helix run, you see the positive stone over here and strong electric field, eastward, westward electric field at high latitude. But if you look at the assimilated result, this kind of feature is very different from that. I will show you the observation as a comparison in the data view graphs. And if you look at this one, this is wide stretch out of the positive stone effect in the low latitude region. And which one is closer to a real observation? If you compare this 16 UT with this one, okay, you see the structure and the stretch of the positive stone in the low latitude. You would stretch out all the way to around 100-degree longitude.
Now, okay. The representation of the observations
yes.
Are honest.
Yes.
And I mean, in a way, I appreciate that.
Yes.
Because you could see all the gaps.
Yes. Yes.
That you have. Because
yes.
You don't have ground stations in the ocean, and you
yes.
don't have ground stations in many territories.
Yes. Yes.
Nevertheless, would there be a way to sort of fill these
the gaps
observations in a way to have a little better an idea how this mapping assimilation
Yeah,
resides.
yes, that's one of the advantage of it. Yeah, well, how you going to fill the gap is very important. You whether have the negative zone in the gap or positive, you don't know.
Yeah.
So yeah, one of the reasons is that even we don't have this system capable of forecast for hours or days. Filling the gap is also one thing that we don't have in the ionosphere community because it's correct. One of the thing have fill the gap would be one good thing too. Yeah.
No, I mean the data assimilation delivers basically how maybe the gap would be filled, is my understanding. But if you could switch to the observations for a second.
Yes.
I mean, I'm almost tempted to get sort of some wet color and sort of paint this through.
Yeah. But if you look at for example, this one, 18 local time, we fill the gap with blue color. It's not a red color one, So there's a physics inside. Well, the idea is that you have a stronger plasma fountain. I will explain it later on. I also have the other example. I will show you. Okay, just.
That's one of the main points here. Is that even if you're just doing an analysis. Superior
Yes.
to simple interpolation.
Yes.
Right?
Yes.
Yes.
Yes. Yes.
So what did you put electric field?
Yes.
What's
Uh, so I'm just showing you that okay. So this is kind of if you look at this model centered on round, you get this positive stone and this plume-like shape occurring in around the mid of the U.S. and Canada area. But using this assimilation, you kind of bring it to the West Coast, and it's kind of a matching with the observation. But most importantly, if you look at this one, this is the same stone day with on the pre-stone day and the stone day with a control. Also, again, the total electron content and electric field, and assimilation one. Okay. And what surprised us was that so when we look at these two after the simulation, we see for example here, we see a strong eastward electric field occurring at the equatorial region. That was not shown over here. Okay. And on the pre-stone day, this a little bit enhancement. This is yellow color compared to green color. So we kind of get this vertical upward drift from this assimilation model from pre-stone day and the stone day, in comparison with the observation that was published during the same stone event at the region where the India located around India. So we get this estimation of the pre-stone day of vertical ion drift around 20. On the stone day, it goes to 75. And this is the number we got from Hillis Fosin, 31 to 78. Weimer, 25 is good, but it's a little bit strong. I shouldn't say a little bit. It's much stronger during the main phase of stone time. But it captured the the feature, the electric field. And remember that the electric field is calculated based on if you change the entire system, you change the electron density, and if you affect the wind, affect the entire system, and then that affects the way the dynamo is or the electric field is. But for this example, we are thinking it may be that we better present the conductivity in the ionosphere. So maybe there's a partial closure of the high latitude currents in the low latitude that perhaps produce this eastward electric field. Okay, this is the result from Weimer. I will show you the result from Healy's forcing, but just skip it with this one. Okay, so those improvement of the electric field at the equatorial region has an impact to that. We do another test for the same stone, but when I say the test is, we run the model in a way that in each hour we forecast 24 hours. So every hour after simulation, we let the model to do the 24-hour forecast for low latitude, mid latitude, and high latitude. And this is using the Healy, this is using the Weimer. And the stone main phase is marked with these vertical white dashed lines. So you show that at the low latitude region, if you consider 70%, there's a magical number. If you consider error, Rubin square difference, error lower than 70% is good for forecast. You can have a good forecast for the low and mid latitude. And you have a little bit for the initial time of the main phase of the stone at the low latitude, but you have very limited in the mid latitude. You almost have no, or I shouldn't say almost, you have no forecast capability for high latitude for this one. Yes?
I understand those are still ensemble.
Yes, yes.
Why the Weimer and the Higgs would be so different? I thought you constrained your ensemble with the observation. Why these two still so much different?
Yeah, I think when we build ensemble, for example, if heat is driven by Kp, we have a Kp spread out a little bit to build ensemble. So for Weimer, it's driven by IMF. We also spread the number of IMF a little bit to construct the ensemble.
Your ensemble is not wide.
Well, I just think that these two, without like a data assimilation like AME, these two high latitude forcing cannot represent the high latitude ionosphere correctly that can be used for forecast. I think. I have no idea. That's a part.
Why are they so different when they're both constrained by observations?
Oh, okay. Yeah. Okay. Yeah, I would.
We're looking at forecast error in PVC.
I think this error are adding up together. If you look at this one, you see they're very different. Because it's not you. Okay, maybe this is just my wild guess. Maybe in each time step you correct it based on what you have, but your data is insufficient to correct it to the reality. And then the next time step, because it's changing so rapidly. So if you look at if we go back to look at the movie and focus on the high latitude, you will see. I mean, they're not. I know in each time step we constrain it to the observation, but it's not in each time step you constrain it to exactly what the reality is.
But doesn't this really tell you, and then that was the other question,
Yes.
tell you that there is a substantial difference in the physics representation in the two models?
Yes.
Somewhere.
So I'm thinking that's so I'm glad that we reached to the first difficulty so quickly, and that's something I want to talk about is that this system can be used for the short range forecast hours for mid and low latitude, but in high latitude I think that's much more complicated. We need to not just using this, perhaps using other more. Oh, here? Okay. No, 24 hours. I'm sorry. 24 hours forecast. So, and yeah, when we right. This is a 24-hour forecast. So each small one is 2 hours. Each small unit is 2 hours. So you cannot. I mean, it's immediately you have a very large error compared to the observation.
Forecasting means the result in
Without data, yes.
Why they're so different is
There's no data. Yes. I was yes.
Initialized by the data simulation,
But you propagate it without. And
compare against observation.
and the free run use the forecast of the. Oh no, for this one because we already know the KP and IMF. But in reality, it will be more difficult because in reality, the forecast you need to use the forecast KP or forecast of the IMF parameter. No.
Mid-latitudes have much more memory than the high latitudes do.
I think so, and it's like, yeah, and I think the low latitude is good because that's kind of a surprise to me because when you look at the ionosphere structure, it's very prominent in low latitude, but when you calculate the difference, okay, so it's, but also because maybe the background is, oh no, this is just only a difference. It's not, yeah.
another thing is the KP says 3 hours. It's not
Right.
good.
Yeah.
Highlight you think that's the
Yeah. I think that's something we need to work on.
But just saying that the ground-based big data can improve focusability of into low latitudes. Yes, but
Yeah.
it's memory issues, but also just the informational content.
Yeah. Yeah.
Are the observations at high, low, and mid latitudes all weighted the same, or are they significantly different?
I think there are also fewer observations. Oh, well, but this is kind of a, if we look at, well, this is a little bit stretch. It's not, yeah. Indeed, there are fewer observations, but the coverage is not bad actually. Yeah, but if you look at here, it's not good. But well, if you look at the number, I don't think the number is the big issue of that. I think because of simply the Healy's forcing and Weimar forcing cannot represent the true ionosphere during the zone. I think that's the main problem. Yeah. Yeah.
Lot of observations in the
Yeah.
south.
Yeah.
None of that then the south forecast would be what worse for the north.
I think this is, when you were just showing, this is virtually unaffected by the data simulation.
Yeah.
This is essentially a straight model run.
Yeah.
Because 12 hours later, when the big storm hits, the ionosphere doesn't keep doing shit. But it's
Yeah.
12 hours ago.
Yeah.
And so what this is telling us is that the model is pretty good at low latitudes, not bad at mid latitudes, but high latitudes are much more distant.
Yeah. Yeah. Yeah.
But it also shows you that you're getting significant improvement for all that work we put into getting the Weimar forcing,
Yes.
among other things, because it has much higher cadence of input, and also because KP is a very, very broad brush. Trying to
Yes.
drive the high latitude. So I think this is very, 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 very informative graphic here, but it doesn't say much about the data part of it. It's
Yeah.
the model.
Yeah.
The geometry of the grid of these models.
The geometry of it?
Yes. Is
I-
it spherical?
It's a spherical,
Yeah.
spherical lat long grid.
Okay.
Handy has a question. Yeah. Or you guys want to go ask a question at the end? Yeah.
It seems the Weimar has a better high latitude, but
Yeah.
somehow the low latitude, even with the same data, the low latitude is not as good as the one with the worst high latitude.
Yes. We need to look into it. We need to look into it. We haven't looked into it. Yeah.
What can do with the TEC? Like
You mean error from TEC?
the fact that there is here the common
I don't think that affects that much because if you look at the TEC from high latitude, it's much smaller than low latitude. So I know that assumption we had is not perfect, but because of number, the magnitude of number is very different. So I don't think that's a reason. Okay. It's good because well, I'd like to have a. It's okay. It's okay. Yeah, please. Yeah. Right. This is not one case for universe. Yes. We need to do more. And honestly speaking, it takes a lot of resource to run this. Yes.
If you can tell us what kind of TIEC version you use, the grid is 5 degree or?
Well, I think it's 1.9A or something. This is not 2.0. This.
It's 5 degree resolution.
I think 5 degree resolution. Yeah. Yeah, it's too expensive. I think in the future we don't want to run 90 ensembles. It's taking too much resource, I think. Okay, we can move to quiet time. Apparently, everybody is very interested in the stone time, but I'm telling you, quiet time is very interesting too. So this is again the observation, but it's a pre-stone period. This is again the total electron content from 2 forcing control run without data, east-wave electric field, and the after simulation. And when we look at this electron density at low latitude, we were very surprised because this was not what we expected to see. You see the red color, the enhance of the total electron content, stretch out in the most of area, but that was not captured by this model run itself. And then if you use these two forcing in a simulation, you produce similar long stretch in the zone direction of the density. And this is what I want to talk to Mike is that, and Stan, that if you do the interpolation, this should be red color, but what it shows is this blue color again. And you see this, it corresponds to this enhance of the east-wave electric field. Okay. Yeah.
It's not stretched as much as the Euler's tail.
Right. Yeah.
So Charles, you have to be careful. You're comparing TC with your density.
Yes.
The height.
Yes.
The hole maybe not that.
Yeah. Yes. We kind of yeah. You have a good point. But this is TC, I know. But we want to make this kind of clear. But this is I think it's probably okay because this is a main contributor to the to a TEC. No.
If you integrate a lot of height.
Yeah. But if you look at this one, it's a similar thing, But it's not the trough. The hole is not that. Yeah. I agree with you that. Yeah. Okay. I was talking about interpolation. Yes. Thank you, Gang. I should be careful for the wordings. So for some of you who is not very familiar with Ionosphere equatorial anomaly, or just briefly tutorial or briefly introduction of it. So Ionosphere vertical, at the equatorial ionosphere vertical drift, it has a daytime upward and nighttime downward. But very special is that during the evening hour, there's a sudden rise of the upward vertical drift before it turns downward. This is what we call as a pre-reversal enhancement, PRE, of the equal speed drift. So for the daytime, you have upward drift that produces a plasma fountain. And then that produces the equatorial anomaly, 2 peaks of the stronger density at the low latitude. But you will still have a plasma supply from the lower altitude because this is during the daytime. You still continue to have a photoionization effect. But during this evening hour, this pre-reversal enhancement of the upward drift move the plasma fountain even higher up, but there's a fewer photoionization over here, and then you produce this trough. And then later, when it turns downward, the layer comes down. These were composed into this in TEC map. So this was shown here. You don't see the trough in the equatorial region, but in the pre-reversal enhancement, you see this two enhanced at low latitude plus this trough over here. So this is a typical, when you look at a GIM or TEC map, you see this feature. This is the feature of the pre-reversal enhancement of the equal speed drift. So I'm plotting over here this the same March 14, 2015. model control run and the prior and the posterior result and the difference. Okay. Yeah, again, there's no blue color trough, so I kind of, yeah, okay. And if we plot this density into the contour lines, overplotting with the electric field in the color map, and you see this pre-reversal enhancement feature of the equatorial anomaly is overlapping with this stronger eastward electric field. Compared to this model control run, this enhancement is like this. It's like roughly 2 millivolt per meter of the eastward electric field. So when we get this kind of a result, we were thinking, okay, what caused that? So if you quickly review the traditional mechanism of the pre-reversal enhancement, this is from Farley et al. Don Farley's paper, 1986. This is the most used diagram to explain this, but our result and R's result shows contrary to this one. Okay, I will show it momentarily. So the idea for this mechanism is that first you have the eastward wind that drives the downward electric field. Okay, and this downward electric field maps to the E region, from F region map to E region along the magnetic field line. So it becomes this direction. And that produces the Hall current and the polarization electric field. And because of the day-night terminator conductivity gradient, you have the polarization electric field. If this polarization electric field, these two guys, maps up to F region again, you will be eastward at the day side and westward in the night side. So this mechanism relies on two things. One is you have this wind-driven downward electric field. And in order to have this one, you cannot have a large E region conductivity, because when you have a large E region conductivity, you will shoot out this electric field. Second is that when you have the polarization electric field due to this Hall conductivity gradient, this electric field in E region is produced due to this Hall conductivity gradient. So the second thing is that you need to have the conductivity gradient in the E region. So so this is one of the famous results from Cathedral-Thiesen's paper, Thiessen et al., 2000, that they reduce the E region conductivity by factors so that they are reproducing this pre-reversal enhancement of equal speed drift in the TIE GCM. So at the beginning, we saw that, okay, maybe we use the data assimilation to improve the conductivity so that improve the pre-reversal enhancement. But the result does not show that way. Okay, again, I'm showing you the overplotting of the TEC in the contour line with the color map of the electric field. And these runs are using the electron density observation and updating all state variables, thermospheric variables, O, N, and T, UV. Okay, and this is the one that we only update the electron density in the model without updating also this the temperature and the winds. And if you look at this electric field, it does not show in this one. So it is not that you improve the electron density so that you improve the conductivity, and then you produce that. You need to also have a neutral wind being updated. Okay, so showing you this result is without updating the winds, control run, prior, and posterior, and the difference. Okay, it's not much change for prior. There is some change on posterior because maybe due to changing of the ion drags. Okay. And the conductivity, the way I plot is like we plot different longitudes, and with I think we're plotting the Patterson conductivity. This is also a run without the neutral wind updated by the assimilated density. So you will see the control and the prior have very similar conductivity gradient. So conductivity is not changing that much, even though you kind of thinking you update the density and you update maybe you change your conductivity, and the difference is not as big as when you update the wind and the difference become like this big. This is kind of, we subtract the conductivity in neighboring longitudes. So this is a difference for neighboring longitudes. Okay, for updating the wind. Yes?
In the conductivity, the density updating through the data conversion.
Yes.
But the neutral atmosphere is not affected.
Right, the neutral density is not adjusted. Only the electron density was adjusted.
So, okay.
Yeah.
So when you adjust the neutral, does it impact the atmosphere again, or?
Yeah, but the way is that we're thinking it will be this way. So if you look at the result that you also adjust the neutral thermospheric temperature and winds, you have this wind change and you have this conductivity change along with it. This is the one result.
I don't understand the basis for the adjustments.
Yes. 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 Okay.
How is that adjusted?
Okay.
You don't have measurements of those.
Okay, yeah. To make it simple is like if you find a linear relationship between the density and the wind, electron plasma density and the wind, and if you move the plasma density to this way, and you kind of you improve the plasma density to this amount, but it will translate to this linear relationship.
So you form a relationship based on the model results.
Yes.
Between the PDC,
The plasma density and the winds.
And the winds and the temperatures and so forth.
Yes, yes.
And then you adjust those according to those.
Yes.
Those are globally derived?
Yes, yes. So it's good at some local time. It's not that good at some local time. So that's one of the things I would collaborate with Wenbin on the issue. I will show you later. Okay, so there's an updating of the pre-reversal enhancement theory. One is from Healy et al. 2012. The general idea is that you have the daytime reverse of the wind from the daytime westward to the evening hour eastward, and then you drive the currents. In the daytime, you have these current loops. So I'm just trying to make it quicker. But in the nighttime, in the evening hour and nighttime, you don't have the E region. So you need to make a current circuit close in the F region so that you will have the eastward current. And that drives the electric field along with it. Okay, but there's another one. If you look at the radar observation of plasma in the evening hour from Hikamaka radar with altitude and time, you actually see this kind of plasma vortex. So when we did this, I coincidentally see R's paper, R's 2 papers published in 2015, and I borrowed this from R's poster to kind of illustrate it. So the idea is that for R's theory is that if you have the wind try in the equatorial anomaly region, that flow in to eastward, and that will bring the plasma along with it. And if you think another way, that you will generate the U cross B electric field, and that will map to the apex of the magnetic field line, and that will bring the plasma flow in the same way. And in order to, you have the plasma going in the eastward. In order to supply this plasma as a source, you need to bring more plasma from lower altitude so that you can make this vortex as a complete loop. So it will be like this one. So our model result is more similar to that because if you look at our wind adjustment, you see the stronger wind over equatorial region, and you have a stronger wind being adjusted throughout the entire latitudes in the F region. But you also, for the control run, you have some troughs at the equatorial anomaly region because of maybe the mechanism that you have more ion-neutral collision at the equatorial anomaly region. But when you see the simulated result, this has moved to a higher latitude because of a polar movement of the equatorial anomaly. And the other thing is that when you have the trough at the equator, that will have a fewer ion drag. So this eastward wind would be enhanced. So the entire system is more, more agree with what R proposed. The mechanism are published by R, and yeah, but we are also thinking whether this will also have a feedback. So in addition, we also want to look at this one in the future. Is that when you have this trough over here, you have a fewer ion drag, so you have a stronger acceleration of the eastward wind at the equator. Would they feedback to the low latitude equatorial anomaly region and make it as the complete system and make the electric field that as strong as what was observed? So that's something we're under investigation. So I'm showing you the Euler result. Okay, here is that. When we have the control wrong, it's this magenta line. It shows very small pre-versal enhancement. If we adjust only the electron density, it gives you some enhancement, but very, very little. But if we adjust the wind together, it will give you this one. And red line is the empirical model of the upward equal speed drift. So when we submit that paper to GIL this year, the reviewer say, okay, you need to compare many days. So we do the 5-day comparison. The blue lines are the upward vertical equal speed drift from Hikamaka observation. The red line is a fair and shirtless empirical model, and red line is from our data simulation. So I think in order to capture this magnitude, it's not bad from the data simulation. It's sometimes overestimated. And when to answer Stan's question that how the relationship between the plasma and the wind works, it may not work so good during the midnight, and maybe that result in this one. But one thing that I have talked to Wenbin is that actually when we look at all the theoretical model, this kind of feature was appearing in almost every model. Just people focus on these little guys, so they overlook this one. So it's actually related to a tide. I think we're.
Why is after the sector seems to be very off?
Yeah, this one. Yeah, this is also something we need to go further to look at it. So I think this also bring our attention to that we sometimes the relationship between the plasma density and the wind is not always good. So one thing we need to do, and we have completed the module, is that we also complete a module to let the system to be capable of assimilating the neutral wind observation. So if we have a Fabry-Perot observation of neutral wind, we are able to. And those wind measured by Fabry-Perot in the pharmacy is mainly nighttime, and that will be very helpful to this. Yeah.
What is it when this blue line is crazy?
Yeah, I was just kind of, the idea for that is you trace the plasma irregularity from you trace the movement of those plasma irregularities. Sometimes if the ionosphere become very noisy, there are small patches, it may cause this one. Yeah, but I'm not the expert of the Hikamaka radar measurement. Maybe Tiger can answer you more because he was a radar person. Okay, he's still a radar person. Okay, so I haven't talked any about COSMIC-2, right? So in my title, I have a COSMIC-2. What I want to show is that for COSMIC-1, we bring a lot of observations, and so that we are building the data assimilation ionosphere. But for COSMIC-2, in addition to electron density observations, we also have the plasma bubble observations. It has this radial occultation soundings over the plasma irregularity. It has a beacon transmitter to transmit signal to ground stations in order to do tomography. Yes, in situ ion velocity and density measurement, you will measure this kind of a plasma bubble showing this fluctuation in density at the satellite orbit height. Okay, so this is a completed story. So since we have built this, we have a data simulation model can represent the pre-versal enhancement greatly. We're thinking, okay, will this impact our model forecast of the plasma bubble growth? So for plasma bubble growth, this is very important because you need to bring the ionosphere layer height up to more than 300 kilometers. So this is one example showing the plasma bubble growth from the semi-3 model. And this is a mechanism. I will just skip it. And it's mainly the radiator instability. You have the current, and on the west side, you have the unstable. On the east side, you have the stable. So that always go this. But the major point is that you need to have this upward trip in order to bring the layer up to more than 300 kilometers. So during the same period of March 14, we observe this plasma bubble structure in these black colors. And these are the instability, plasma instability, very high, possibly driven by the pre-reversal enhancement. That bring the ionosphere layer to very high. And during the storm period, we also plot this GPS or GNSS signal fluctuations. So here, the pre-storm day, you see the 20 local time, 21, 22, and red color shows the fluctuation of the GPS signals. That means there's very highly possibly you have the plasma irregularity over there. And if we plot out in different longitudes with local time, you will show that in almost every longitude you have it. It has every longitude has the plasma bubble producing the GPS signal fluctuation. On the storm day, a little bit different. For example, India got very strong plasma irregularity, but Taiwan used to have the fluctuation before storm day become quiet. What caused that? But before seeing what caused that, we just calculate the plasma bubble growth rate from the data simulation output. I plot out the example from the Weimer forcing run, and this red color means highly possible there's a plasma bubble growth. And there's an hour difference. This is like a 19 to 20 local time, showing that possibly you have a plasma bubble growth. But you need to take 1 or 2 hours to have the plasma bubble to really grow. So 2 hours difference is good, okay. And for this, on the storm day, you will see pre-storm day in Taiwan and Japan sector, there's activity. But during the storm day, there's no activity from observation and from data simulation model. On the contrary, you see very strong activity in observation and the model prediction from the simulation system. So again, showing you here, day-to-day, red means from Taiwan, 120-degree longitude, and the blue means India. So on the pre-storm day, they are similar. Storm day, they are very different. Stronger in India, very, very weak in Taiwan. And you see this no assimilation and assimilation. No assimilation in dashed line show opposite. Taiwan should have a stronger activity than India. But after assimilation, with these solid lines, it shows close to the reality. Yeah. Yeah, well, I'll show you later plots. Okay, so we are investigating that. This is a pre-storm day in the Taiwan sector, India, and this is from the storm day. And this, again, plot out the eastward electric field and meridional winds. You see this layer is modified by this electric field. So this strong electric field producing this kind of layer. But what caused that is that if we plot out the field line integration of the density, that's one important driver for the radiator instability. And you plot out the gradient with altitude, you see this large gradient occur about 300 kilometers. But during the storm day, at the 120-degree east, this goes down to 250. And this remains high to almost 400 kilometers. And if you look at the electric field, they agree with each other. So how about globally? We plot out the model prediction of bubble growth in the vertical and observation in the horizontal. And this red box means if you model says there should be bubble, and they're really bubble observed, this model says no bubble and there's no bubble observed. These two are not good. These two are good. So these are control. These are assimilated. Most of the dots are moved to these two areas after the assimilation compared to a control run. Okay, so this is something that is also useful to it. If you still have some, if you want to look at it, we also do the recent September storm, but I'll just skip it because it's already quite lengthy. I want to show you this nice picture. What's the impact of it for ionosphere community? Ionosphere modification is considered, I learned from my colleague from Aerospace Engineering Department in NCKU, that they are doing the GNSS based guiding system for aviation navigation. So the idea is that traditionally airplane follow the ground stations. So, but if you use the GNSS based one, you don't need to rely on it. Okay, and from the community, they told me that the ionosphere is the main driver for it. This is one example. If you want to land in on the JFK airport, traditionally it goes this way. But it should be able to go this way with GNSS aviation. This is more extreme. If you go to Florida, it go like this way. But indeed, with the GNSS space, you can go this way. And for that community, they think, well, in several of their papers, they often write this. Ionosphere is the main error source for having this aviation navigation possible. But next generation is moving on, so they will be happening. Okay, yeah. So I'll just summarize. I think I have a lot of things already. Get tired. And I'll just quickly summarize it. The dot TIGCM shows encouraging result at low latitude and mid latitude. And neutral wind is very critical. So it's critical for having it updated and also having it as a new observation source. But I want to mention one thing is that in order to make it possible in a simulation system, you need to have a measurement on real time within 1 or 2 hours. Otherwise, it's considered useless. Okay. And then high latitude is very challenging. Okay, we all know about it. We have a very good discussion on it. And the observation is still insufficient. I count the number of this one. When you look at the COSMIC-1 observation, it's 1 day you have that. But if you divide by 24 hours, yeah. The way we do the 10-minute update, we actually every 10 minutes we update 1 hour data prior to that. If we update only 10-minute data, it would be much worse than that. So I count the number of the observation from the ionosphere. It's a few tens thousands, but for atmosphere, whether I think millions observations per day, I think. For weather forecast, 14 to 16 million. 40 to 60, okay. So that's larger difference than I saw. In 6-hour window, okay. I count our numbers is, several tens thousand observations. When you look at the thousands of ground-based GPS observation, they are not real because you only can count the real-time observation. That was down to hundreds of observation stations. So if you indeed count, there's big difference. Still, this gap is, observation numbers. But I have to make the point very clear that observation number need to be operational. We are expecting ICON to provide wins for research mode, but for operation mode, we need to have it within hours. Okay, so that summarizes my talk. So this is the data simulation output, and the data simulation output does predict or forecast bubble occurrence, and we do observe them. So that summarizes my talk today. Thank you for your attention. So everybody is lost. Yes.
Just to comment
Yes.
night side.
Yes.
Correction of
Yes.
neutral lines with
Yes.
big data.
Yes.
So probably relation surface now could
Yes.
Maybe you could actually, maybe a simulation of tech data is making things worse on that side.
Yeah. So
maybe you can decoordinate.
Okay. We can try to having it as a different time window instead of a like a turn it on or out. Okay. Yeah.
Make that localization
Yeah.
before
Yeah.
using the same.
Yeah. Actually, what Sue mentioned in the afternoon, early afternoon, so there are two time periods. The correlation is not good: midnight and the early afternoon. We actually answer the reviewer by plotting out those relationship. It's like a thread in that two time period. Yeah. Stan, yes.
But what you really need is more neutral wind and probably composition,
Yes.
intensity,
Yes.
observations.
Yes.
To improve things. And I think that message needs to be well documented and proven with appropriate model runs because as NASA enters a new planning cycle, those facts have to be brought forward to emphasize the importance.
Okay.
You said right at the beginning, where you pointed out that if you only updated an hourly cycle, it's almost
Right.
Data. That tells us something about ionospheric resistance and lack thereof. And it just strikes me that between the difficulty of knowing what the solar wind is going to do now it's in the house, and the difficulty in the ionosphere not having a very long memory, that the longer range forecasting is incredibly difficult.
Yeah.
And therefore, we really ought to focus on the possible, which is the short-term forecast, which requires real-time data cycle, as you pointed out.
Yes.
I think all of these facts need to, I don't know if they're facts or not, but all of these things that we all think are true need to be effectively communicated to the level.
Yeah, I think two things that I only dare to say, okay, we can do 3 to 6 hour forecast in mid and low latitude. Okay, that's one thing. Yes. Yeah. Second thing is that I think, according to Mike and our others' comments, that having the ionosphere map in real time at the current time nowcast is also good. It's what we don't have. Believe me, because I believe a lot of us were doing the ionosphere observation during the great solar eclipse in August 21st. It took us like 2 days or 1 day after to get a map. 1 day after, if you do it really quickly. If you wait out all the data to come out, you brought a map. Okay, 2 days because we were doing it. So I know that. So having it to having it at the real time and now is also something that we don't have currently. Yeah. So I think that's also.
Things like game, right? I mean, there's non-physics-based approaches.
Yes. We also.
I mean, operational game.
Yes. Ghost Marco, common filter. Yeah.
And there's the various interpolation approaches.
Yeah.
They're effective, but I think physics-based nowcast is certainly within our grasp.
Yeah.
It just has to be implemented in a data system.
Yeah. Oh, I when you talk about this, I found that I overlooked this summary. Traditionally, people think ionosphere data simulation cannot do physics, but for the pre-versal enhancement study, I think this is also very helpful to identify what physics is operating when you have a system more closely to the reality. Yes.
Starting bubbles suppressed during the recovery phase of geomagnetic storms.
Yes.
Are bubbles suppressed during the recovery phase of geomagnetic storms? I mean, that's what you think is secret.
It depends on the phase. You can also have a depressed because if you have the penetration industrial field at the time when you have a suppress of a pre-versal enhancement, it depends on where you are and what local time sector you are. And
depends on the season. So there's somewhere so-called a seeding factor. So my sample longitude.
So I would say that local time and longitude. Yeah, I have a feeling that yeah, what I showed was March. I haven't. It would be interesting to show August, where you expect fewer, or July, where you expect fewer bubble. And yeah.
The day after this,
Yeah.
semantic space drop is really not
Yeah. Yeah. I think another time we talk about, okay, stone time need to be prepared for probably produce a plasma bubble, affect the commutation. But for this case, no. Stone time. My student did a positioning for this case. Stone time, no bubble in Taiwan. Perfect navigation for the GPS. I was like, okay, that's good. Yeah. Yeah. The next one? This one. Right.
This is the 6 linear rotation that projects bubbles or what?
Yeah. Yeah.
Have you looked on the 17th and 18th of March? It's gone, right?
I mean the later day. Yeah.
The recovery period is
Yeah, I haven't. No, I haven't done it.
So
Yeah.
maybe it's the disturbance dynamo in some ways suppressing the formation
Yeah.
of bubbles.
Yeah. Yeah.
Stone by stone.
Well, maybe not.
Yeah.
Haven't seen these days before they were stored.
A lot of people did statistics.
Oh right, I want to show you this one. Sorry, I would. So, I'm sorry, Mike. I would just give you for this event. I'm sorry. For this recent event. Okay, this is a pre-stone day. 5 UT, 11 UT, and these are the stone day. And you don't see the pre-versal enhancement. And by looking at this, I told my student, I don't think there's a bubble. And I asked them to check the data. There's no bubble at all. So this is kind of a good thing that you can, well, it's not perfect, but you can have some idea what might happen, what might be happening. Yeah. Okay, Mike.
So now I learned, I think, from this presentation that we will never have like numerical weather forecasting, a 5-day forecast capability, which weather forecasting we pretty much have now most of the time, because the ionosphere just doesn't have a memory.
Not long enough. Yeah.
But you're demonstrating that this field is moving to a capability that that you will be able to do, assuming for a minute the solar wind is steady, to forecast the development of the ionosphere basically up to what the memory is.
Yeah.
Now, if I would dream for a minute that we would have perfect data assimilation of the release of a CME, the modification of the solar wind flow, what kind of maximum typical forecast times do you envision in having the heliospheric modeling included?
Yeah, as I mentioned that if we have we now use the forecast KP. So if we have have an idea of what KP or DSC might be, we might have a chance to try on it. But I want to say the other thing is that using the current amount of observation, it's only hours. But I don't know if we have a 40 million observation per 6 hours. I don't know how far we can push it to the range.
And also I want to, like Charles focused on actually quite strong storms
Yes.
to make a statement about predictability. But I've been looking at a bit more quiet time, or actually mostly quiet time, and then atmospheric predictability, the impact of tech data and cosmic data of the atmospheric predictability in terms of compositions and then temperatures. And then there is a skill in doing this kind of data assimilation exercise beyond a day or two on the neutral part, which is kind of hidden here because the compositions and then temperatures, well, mostly composition, are corrected by this simulation system that is actually helping forecast. But it's because it's so driven period that Charles has focused on. So it's kind of it's masked. But there's still.
Yeah, we this
My question is, if I add to that, and I hear that, that's good. So you say 2 days maybe.
Beyond that, yeah.
But if I add to that, I release a big CME towards Earth now, and I can perfectly give you all the data that's.
You mean all the data of CME or ionosphere?
Yeah,
of the CME.
He's going to solve the solar wind problem for you.
Given the
Stipulating that, what's the
model, what is then the forecast time that you can give?
Okay, I think I understand Mike's question. Actually, for what we do here, we presume that we know all about the solar wind effect. So what I presented here, when I show this one, we know every DST-KP. We don't use the forecast DST-KP. So this is a case. This kind of forecast capability is based on that. If we know precisely what the forcing from the sun would be, and I'm sorry that I'm sorry that it's not very encouraging. So during the stone time, it's only hours. If you go to a later main phase, probably 1 or 2 hours in mid-altitude. So this is a perfect case. We have a perfect forcing from the solar wind. Right. So maybe this is kind of a.
Let me get a different answer to Mike's question.
Yes.
Because you're asking an idealized question. And in principle, the same reason that the ionosphere doesn't have a long memory is also a positive thing, because it's a very highly driven system.
Yeah.
And consequently, if your model is perfect, or nearly so, it can represent the processes and you have a quantification of the driving, then you have very good ability to forecast the result. So in the stipulation that the solar wind interplanetary magnetic field problem is somehow solved, and we know that drive. The other thing that drives the ionosphere is interactions with the entire atmosphere, especially the lower and middle atmosphere. And again, in principle, we have very good forecasts on a 5 to 10 day basis. Past that, we know it's a chaotic system. Ultimately, there is some limit to the forecastability. But in the ionosphere, in principle, there is no such limit. If you can forecast the troposphere and the middle atmosphere for 5 days, and you can somehow forecast solar chaotic environments for 5 days, you could get with an excellent model, get a good forecast of the ionosphere for 5 days as well. I think that's in principle.
Okay.
So is then this basically documentation that there's something wrong with these models?
Yes. Oh yeah. The models are far less than perfect, but you can see how much improvement was made from a 10-year-old model on the left to a 3-year-old model on the right. Now, I can tell you that the latest model, we run it at 2.5 degrees. We're getting a much better ionosphere just from the increasing resolution. And this recent work that Conductivity has done, driving into 1 degree and lower, it's really quite impressive. The model physics are not that bad, but they are far less than perfect. And so consequently, this is the rationale for trying to improve all the little details that go to those physics, and also you have the need to capture all of these scales, especially if you're going to do classical bubbles. You have to have extremely high.
Yeah, I do see the TIG EGCM 2.0. It produced much better equatorial anomaly than
much finer
Yes.
Resolution index.
Separated one, yeah.
More or less better, the ton of ionization. It really
Yeah.
improved. When we were getting ready to release a model, when we said, no more 5 degrees, right? It's fine for neutral atmosphere.
But it's very expensive, you know.
It's 16 times more expensive.
Yeah.
The Weimar still empirical.
The Weimar is an empirical representation of what happens to the magnetosphere given measured forcing. And of course, the measured forcing is not perfect either because ACE is not really upstream of the magnetosphere. And is also subject to measurement error. And then, of course, if you had a theoretical model of the magnetosphere, it might or might not be any better than Weimar. And so that whole side of it is even less perfect than this model. But you know, in principle, Michael's question drives at the idea: if you could specify the forcing, what can you do? And my answer is, if you could specify the forcing and the fundamental physics, get all the details right in the model, that the ionosphere forecast problem is a solvable problem.
Right, like in low latitude, I just imagine
Not
that.
that there's some chaotic process going on that we don't understand that's going
Yeah,
to the whole thing go haywire, which is the case in the troposphere.
But an important corollary there is you need hourly updates of your data in a driven system like that. So that drives your ground station.
Yeah.
When you say real-time observation
Yeah.
from COSMIC-2, we don't have the ground stations to get us hourly updates.
Well, actually, they are like a 300 real-time ground station together. So
that's several hours.
for the COSMIC-2, actually based on we were asked by NOAA that what time latency would be good. We told them that not longer than 30 minutes. But because of ground station difficulty, they make it as a median value, not longer than 30 minutes. At the beginning, it was a mean of the 30 minutes. Now it's changed to median. Yeah.
Can we?
Yeah.
We're already 20 minutes over. I think we should thank Charles again and continue discussing offline.
Okay.
So you ran this with
Sorry?
you ran